Deep inside your phone, your computer, pretty much every piece of modern tech, there's this tiny, absolutely brilliant component. It's called the PN Junction, and it works like a perfect one-way street for electricity. It's literally the foundation of our entire digital world.
But that begs a really cool question, right? How in the world can you build a solid thing that lets electricity flow one way, but just slams the door shut if it tries to go backwards? Well, the answer is all in the beautiful physics of the PN junction.
Okay, so it all starts with a pure semiconductor, usually silicon. We then intentionally add some specific impurities, that's a process called doping, to change its properties in two very different ways. On one side, we make what's called P-type material. It's full of these things we call holes. Just think of them as little mobile positive charges. And on the other side, we make N-type material, which is just loaded with extra mobile electrons, or negative charges. Now, by themselves, they're kind of interesting, but the real magic happens when you bring them together.
All right, so the second these two materials touch, things get going. All those extra electrons from the N side see the holes on the P side, and they rush right over to fill them in. Right where they meet, at the junction, they combine and basically cancel each other out. This creates a little area that is suddenly empty or depleted of any mobile charges, and that is what we call the depletion zone. It's super important.
Okay, but this depletion zone, it does something really powerful. The atoms left behind on the N side are now positive ions, and the ones on the P side are negative ions. The separation of charge creates its own little internal electric field. And what does that field do? It creates a built-in voltage that acts kind of like a hill, stopping any more charges from just wandering across. So now, the system is stable. It's at equilibrium. So the junction just sits there, naturally blocking the flow. But what if we try to force the issue? What happens if we hook up a battery in the wrong direction, what we call a reverse bias, and try to push current against the natural grain?
You'd think you could just push through it, right? But nope, you actually make the barrier stronger. The reverse voltage yanks the electrons and holes even further away from the junction. This makes that depletion zone wider, and that internal electric hill gets even taller and steeper. You've basically just flipped the switch to off, and only a teeny tiny leakage current can get through.
And this has a really fascinating side effect. Because we've separated all these positive and negative charges across an insulating zone, the junction actually starts to act just like a capacitor, storing up electrical energy. The source material puts it perfectly. Its behavior is no different from a parallel plate capacitor. It's a dynamic little barrier.
So this electrical wall seems pretty solid. But come on, every wall has a limit, right? What happens if we just keep cranking up that reverse voltage, pushing harder and harder and harder against that junction? What's its breaking point?
Well, at a certain critical voltage, that barrier gives up. And it doesn't just fail, it fails spectacularly. The current, which was basically zero, suddenly floods through in this massive uncontrolled rush. This is known as breakdown. And yeah, the one-way street just got completely demolished.
But here's where it gets really cool. The breakdown isn't just one simple event. This barrier can fail in two totally different ways, and it all depends on how the diode was made. One way is like a brute force, physical chain reaction. The other relies on the wonderfully strange rules of quantum mechanics. First up, Avalanche Breakdown. Picture a single charge carrier sitting in that wide depletion zone. The huge reverse voltage acts like a slingshot, launching it at an incredible speed. It gets so much energy that when it inevitably slams into an atom, it knocks a whole new electron-hole pair free. We call that impact ionization. So now you don't have one carrier, you have three. And they're all accelerating, causing more collisions, making more carriers. And you get this explosive chain reaction, a true valanga, or avalanche of current.
Now, the second way it can fail, well, this is where things get straight up weird. We have to dive into the bizarre world of quantum mechanics. The source material calls it a purely quantum phenomenon, saying it's as if the electrons were passing through a tunnel under the barrier, not even trying to go over it. This is Zener Breakdown.
So the whole secret to Zener Breakdown is this. In diodes that are really heavily doped, that depletion zone is naturally super thin. So when you apply that reverse voltage, the barrier becomes an incredibly steep and narrow wall. It gets so thin, in fact, that electrons can just tap into the weirdness of quantum mechanics and poof, appear on the other side. They literally tunnel through a barrier that, according to classical physics, they should have zero chance of ever crossing.
Okay, so let's put these two side by side. Avalanche breakdown, that happens in diodes with lighter doping and wider barriers. And you usually need a higher voltage to kick it off. Think more than 5 or 6 volts. Zener Breakdown is the star in heavily doped diodes with really thin barriers, and it happens at lower voltages. And get this, as things heat up, it actually gets harder to cause an avalanche, but it gets easier to trigger a Zener Breakdown.
So you hear catastrophic failure and you think, well, that's bad, right? I mean, that's something engineers must try to avoid like the plague. But what if a failure could actually be predictable? What if you could turn a flaw into a feature?
And this is where the genius comes in. Engineers took the super predictable nature of Zener Breakdown and designed special Zener diodes that are meant to operate right in that breakdown region. Because it happens at such a precise and known voltage, they can be used as perfect voltage clamps or limiters, protecting all our sensitive electronics from dangerous voltage spikes. What started as a failure is now one of our most important protective features.
You know, this whole journey from a simple component to its absolute breaking point, and then turning that failure into a vital function, it's just a perfect example of how innovation works. Sometimes understanding the limits of a system is the key to the next big thing. It really makes you think, doesn't it? What other so-called physical failures are just waiting out there, not as problems, but as the next breakthrough waiting to be discovered?